Hello, and welcome to our online training for students presented by Doable Software. Today we will be working with our FEA and design software RFM6, and the goal of this training is to provide you guys, students, with the fundamental knowledge needed to model/work with any type of basic structure, view results, and understand fundamental basic theories of FEA software. So within this training, we'll be working with simple models that will be used to understand these concepts. My name is Alex Bacon, and I will be your trainer for today, and I'm joined with my colleague Siska Choya, who will be moderating. We are both technical support engineers and are located in our Philadelphia, Pennsylvania office. Here you can see the control panel. This will be used throughout the training. You can show or hide this panel as well as adjust audio settings. There is a chat box and questions panel within this panel where you can ask questions. Make sure if you are sending a chat that this is set to organizers only. This training is intended for you to just listen, but you can model along if you would like. Cisco will answer any easier questions that are possible to answer through the chat and save more complex ones that could have some discussion with them for the breaks. This is where questions will be answered and discussed, and so we'll save that time for right before the breaks. With that said, there are 2 breaks planned throughout the training, one 5-minute break at 2 p.m. Eastern Standard Time, so 1 hour within the training, and then a second 5-minute break at 3 p.m. Eastern Standard Time at the second hour of the training. Here is the content for today's training that I plan to go through with you guys. So the first topic will be the basic principles of FEA. And then the second topic will be an introductory example, and that will include a continuous slab, which is where we'll start to get into RFEM and get into a little bit of modeling. The third topic is going to be plate theory. The fourth topic is going to be all about nonlinear calculations. And then the last topic where we'll talk all about singularities. So with that said, let's just jump right into it, into our first topic, and we'll just start going over the basics of FEA or finite element analysis. So to start off, computer software or computer programs are based on the displacement method. So another method that you might be aware of is the force method, where the unknown is the force and the internal forces must be calculated based on this. And with the displacement method, you can calculate the displacement vectors and then the internal forces and support reactions. And also, and most of the times, analytical solutions can be difficult with large, complicated structures. And so this is where FEA comes into play. And so doing hand calculations are almost impossible with these large, complicated structures, and the limits for what is possible with regards to complicated structures and hand calculating the results for these are being reached. So this is where FEA software is required, like I said. And with these structures, they are modeled. These complicated structures are modeled and converted into finite interconnected element meshes. And then the material and the cross-section properties are given at each of these FE nodes within the element mesh. And then lastly, the mechanical behavior is transferred between the elements. There is a word called discretization, and this is a word I would like you guys to know and walk away with. The meaning of this word is the act of structures being submeshed into finite elements. So this is what I just explained right there. The next thing to briefly get into is the FEA calculation workflow. Now, I'm no expert on this, and I just want to give you guys the overview and the basic general knowledge of how the workflow is listed in step-by-step form and how it works within an FEA calculation. So the first step that the program goes through is determining the local element stiffness properties. And then second, the program changes stiffness properties at each node and converts this into the global coordinate system. Then the composition of the entire structure takes place. Boundary conditions or supports are then defined, and these can consist of sliding supports, rigid supports, and hinge supports, as you may be aware of, for example. And then fifth, the displacement vectors can be determined by solving for the system of equations, just like we spoke about. And lastly, the support forces and internal forces can be determined, aka the results of the structure. So with that said, with the general knowledge of how the workflow works for FEA, we can dive into our next example, which will be our continuous plate example. And for this, we are going to use this example to compare results of the bending moment from the plates to the continuous beam. So this will kind of give us an idea of what results we should expect from the continuous beam. And so with that, we can jump into RFEM. But before we do, I would like to give a poll just to gauge how familiar everyone is with RFEM, whether they've used it or never heard of it. So I'm going to launch that poll now. So you should see that poll open up on your screen. And I just would like to gauge the familiarity with RFEM with everyone. All right, so it looks like 93% of you voted so far. And it looks like about half of you, a little over half, are beginners, and maybe some of you are average at RFEM or familiar with RFEM, so that's good to know. So I'm going to share that poll so everyone can see and gauge the level of which everyone is skilled at. So I'm going to hide that now. And now we can jump into the program. So I'm going to open up RFEM 6. And again, just to go over what RFEM is. RFEM is a structural analysis software that is capable of analyzing plates, members, and solids. So results like deformation, stresses, internal forces, these can all be calculated on 1D, 2D, and even 3D structures. So almost anything is possible with regards to finding results for a structure. Even this can even include calculating the volume and weight of a structure. And here on my screen, you can see that we have an already modeled structure. This is our plate example, which we will be modeling in just a little bit. But I would just like to go over the general UI and just kind of get a feel for the software before we get into any modeling. So on the left-hand side here, you can see we have what's called our navigator panel. And within this navigator panel, this is very important. This is where all of our model data is organized into these expandable and collapsible folders. So here you can see we have our basic objects, special objects, and then we have some specific tools that we can use for nodes. We will get into this later, but if I expand the basic objects here, You can see here is where all of our materials for our model are listed, sections are listed, we have our thicknesses, nodes, and everything here can be clicked on and is synced up with RFEM and the work window. And so this is just kind of a great way to just check and see where everything is located within your model and what is in your model. So you can again see members here, surfaces, and everything is numbered to organize. Next we have down here our tables. So the tables, this is also where data can be viewed and edited, similar to the navigator, but within the tables, data can be edited numerically using numerical input. So right now we're looking at our static analysis, but we can change this to just the structure. So if we change the table here to structure, we can view all of our model data here listed and organized in these tabs down here. And basically anything can be edited down to the coordinates of a node. So if I go to basic objects and node, you can see we have our coordinates for our nodes here, and these can all be adjusted. Also within the tables is where if any design work is being done, this is where all of the input data and results are going to be shown down here in the tables. Next, you may notice that my background in my work window is white. Sometimes it can be black by default, if you've just recently downloaded RFEM. The color of the background can be changed to whatever you would like. So for example, if you go up here to options and you prefer a black background or a white background, that's under display properties here. And the general category, we have background here. And then you can see you can change your background color to basically almost any color you'd like. So I'm going to keep mine as white, as I think for presenting it allows you guys to more easily see what I'm working with. And that leads into the work window. So here's the work window. I can rotate my model, I can play around with it, I can manipulate it. So the work window is where almost all of your modeling will get done. Right now I have my grid turned off. If I turn my grid back on down here, you can see I have my grid points and everything. So this is basically where all of our work will be done and all the modeling will be done. Up here in the toolbar, this is our toolbar. We have all of our tools listed up here. They're all organized into these categories, which can be moved and manipulated. The toolbar can be customizable and you can move things around to your liking. If you want your toolbar to look like this and organized, you can just simply right click in any of the blank space here, hit the reset menus and toolbars to default, hit yes, and your toolbar should be reorganized to the default setting. And everything should be snapped back into place if it ever gets out of order. Next, we have our insert menu, our menu bar up here, which should look familiar to other programs. We have the insert menu here, and this insert menu basically organizes all of the functions you see on the toolbar here, all the tools into a menu if you're having trouble looking for something, such as basic objects. Maybe you just want to create a node and create that graphically. Instead of hitting the create new node button, you couldn't find it, you can use the insert menu. Then next we have the views up here. So you can use these view buttons up here to change the view of your model, like so. And we also have a new addition is the cube up here, which also allows you to change your views as well. So this is one way to look and change the view of your structure. You can also hit this button and it will give you a isometric view as well. Next, in the navigator here, right now, we're looking at the data panel. So there's 3 tabs down here in the navigator, multiple tabs. So this first tab is called data. Second tab is called display. And within this display tab, I can collapse all of these subcategories here. So we have subcategories such as model, results, and within this display tab, this just allows you to turn graphically off and on anything that's shown in the window here. It doesn't deactivate or remove anything from your model structurally. It just deactivates the graphics. So if I went under model here, and let's say I turned off surfaces, so you can see the surfaces disappear. This doesn't actually remove the surfaces from the structural analysis portion, it just turns off the graphics. So basically, here is just where you can turn on and off things graphically. You can turn numbering on and off. So that's the display tab. It's kind of where you'll find all of that stuff. Next, we have views tab. This works a little bit similarly to the display tab, but with a function called visibilities, this can be activated. And now you'll see once I activate visibilities, I don't have anything visible to me in my model that's deactivated. But let's say I only wanted to view surfaces that have a concrete material. You can see once just going to ignore that. Once I activate the, okay, so a little bit of crash there. Let's just reopen RFEM by closing out of that. And we can open RFEM back up. Sorry, everybody. 1 second. And while that's opening up, should only take a couple seconds, we can give a poll. So the next poll I was going to give is this question. So throughout the training, I will be giving questions, and I would like to give this question. So that will launch now. And if everyone could read it and answer it, and then we can go over the results and correct answer afterwards. I'll give everyone a minute to do that, and we can continue after that. All right, so let's go over the results to that question. So I'm going to close it now and share the results. So the question was, what is the definition of discretization? And the first answer was a structure that is converted into finite elements. Second option was the calculation of a structure according to FEA, or the submeshing finite elements into smaller elements. So actually the correct answer is a structure that is converted into finite elements. The submeshing of finite elements into smaller elements is actually not correct. So yeah, discretization is taking a complicated model or just a structure or a building and then throwing that into an FEA software such as RFEM and having that software submesh all of the elements of that building into finite elements. So that's discretization. And yeah, so I'm going to hide that. And now jumping back into RFEM, the next thing I just want to do is just quickly run a analysis. So we're just going to run the results of this model real quick. And then we're just going to quickly go over the results, nothing in detail. So just wanted to show you that once the results are run, that this fourth tab here in the navigator panel is going to appear. As you may have seen before, we only had 3 tabs, but now the results have ran, we have 4 tabs. And then you're going to see these collapsible categories here. So we can either show our deformations, we can show member results, surface results. And this is how you manipulate and turn on and off the results you would like to see in the work window on the right-hand side here. So things like member internal forces, such as normal axial forces or normal forces, shear forces, moment, torsional moments, things like that you can view on your members. And same with surfaces, you have our internal forces and stresses and etc. And also, again, when you're manipulating your model within the window here, you can, if you have a mouse that has a scroll wheel, you can click down on that middle button, on that scroll wheel button, to move your model in translation. You can hold Control and click on the middle mouse button to rotate the model, and then you can use that scroll wheel to zoom in and out. One last function I'd just like to highlight is highlighting. And so with highlighting, you can highlight from right to left, and highlighting from right to left will select anything that touches this box here. Highlighting from left to right will only select elements that are fully within the boundaries of that highlighting box. So you can see how that works. All right, so one last question I would just like to ask before we get into modeling the continuous plate. So I'm going to post that question and then we can dive right into that. So I'll give everyone about a minute to answer that, and then we can go over the results afterwards. All right, so it looks like 93% of you voted. So let's just show those results real quick. So what is RFEM? First option, it is a 3D structural frame analysis program. Second option, it's a 3D FEA program for calculating members, plates, and shells. And then the last option, it's a 3D FEA program only for calculating members. So the second option is correct. Looks like most of you got that one correct, so nice job. It's a 3D FEA program for calculating members, plates, and shells. The first option, 3D structural frame analysis program. So the problem with that option is that it is not just a 3D structural, it's not just for structures with that, it's not just for frame structures, it also can incorporate or model plates and solids as well. So, and then the last option is it's also can calculate surfaces and solids. So I'm going to close that. And now we can begin with modeling our model that's here, basically. So the first thing you want to do when first starting to begin to model something is you want to either go up to here to File and click New, or you can just click on the New Model button here in the toolbar. So we'll click on that, and our dialog box here called New Model Base Data will open up. And so basically we just want to go through this first tab, this first main tab here under this base data dialog box, and give our model a name. So this model, I'm just going to name it continuous plate example, and we'll leave it at that. There's an option to give the model a description. This isn't required, but you can give the model a description if you'd like. Then down here, we have the type of model. We can either pick from 3D or 2D models, whether you'd like that 2D model to just be in the XZ plane or XY plane. You can pick whether you want it to be a 3D 2D model. It sounds kind of confusing, but basically this just means that forces and reactions and internal forces can take place out of plane, or plane stresses kind of lock all of those stresses and reaction forces within that plane. So that's kind of the difference between those two, or you can also just do a 1D model if you'd like as well. For this model, we'll be sticking with 3D. You can also save models as templates and open them as templates over here on the right-hand side. And that's kind of the gist for this first tab here. Everything else we can leave as default. Next tab here is the add-ons for design. Within this training, we're not going to be going over any design, but we will be using one of these add-ons later, so this will come into play. For this training, also, we're not going to be using, or we're not going to be generating load cases or load combinations based on any particular standard, so we can turn off the classification, standards for classification and wizards options here, so we don't need to generate any load cases or actions or combinations according to any standard. So we're just going to leave this as a general analysis. Next tab here is standards. This is where if you did check these on, you could pick from a list of standards. We have American standards, Canadian, European. So all of those are listed and can be found here. And so that's how you would determine what you would want your load cases and combinations to be generated according to, for example, the ASC 7 or the European standard or Canadian standards. So next, standards 2 we don't need to worry about. The only other bit of information that we need to get into is under settings and options here. So I'm going to just make sure that my global axis is set to upward and that my local axis system is set to upward as well. So we have our global axes, and that's always going to be indicated by a capital X, Y, and Z. And then we have our local axes, which is for every surface and member has a local axis. And it's always indicated by lowercase x, y, and z. So we'll keep that as upward. And now Everything else we don't need to worry about. These other tabs we're going to skip for now. And all we need to do now is click OK. So once we click OK, a blank model will open up. Sometimes materials from other models can be carried over into this blank model. So I'm just going to go under here and delete those. Maybe some other sections can be carried over as well that are previously defined. I'm also going to delete those along with some thicknesses that were defined as well. So now you can see in my work window, I just have a blank grid here. Now this grid can be customized. So let's go into the settings for the grid plane here. You can see we have grid points here. So if we go up here to this button, settings of work plane, grid/snap, etc. If we click on this, we can take a look at our settings for our grid here. So right now, at this moment, the basic information is that we have grid 50 by 50 grid points here. Right now, my units are in meters, as you can see. So those points are spaced by meters. I know this is an international training, so that's why I want to show you that we can switch between imperial units and metric units. And to do that, you can almost do that in any dialog box. So you can see there's this button down here, units and decimal places. If we click on that button, you can see under model for all of my units that are related to modeling, they're all in metric right now. So you can take almost any model and at any point change it from imperial to metric to imperial or vice versa by going down here to this button that says load saved template. And under load saved template, we can click on imperial here. You can see I have that set to default, click OK. And so this is how you can switch between imperial or metric units at any point. So I'll click OK again. And now you can see that the spacing and everything is in feet now. So I have a grid here that is a 50 by 50 in grid points in each direction. And those grid points are spaced out by 1 foot. For this model, I would like to change this from 50 by 50 to 100 by 100. So we can take that and I can just copy and paste the rest of this. So in the positive and negative direction and in directions 1 and 2, which you can see in this graphic over here on the right hand side to help you understand that, it's going to be basically a 100 by 100 grid. So I'm going to click OK. And now you can see my grid here is, just going to save this real quick. You can see my grid here is 100 by 100 now. And yeah, so now that we have the grid set up correctly, we can start to just model our first continuous plate. So I'm going to zoom in here and I'm going to go up here to new rectangular surface. And this is the first tool that we want to use. So I'm going to click on new rectangular surface to create this continuous plate. And now you can see this dialog box will pop up called new rectangular surface. And then we just need to define a material for this surface and a thickness for this surface. So first, we need to define a thickness. So I'm going to click on create a new thickness here. And the new thickness dialog box will pop up. So basically with the thickness, you can see what that is defining on the right hand side here. Normally you can think about this as with a beam member or column. That column requires a material and a cross section. So as an analogy, you can think of the thickness as the cross section and then we just need to give it a material. So every surface requires a thickness and material. So we're going to make the thickness of this surface 12 inches. And then we're going to go here to material. And when choosing a material, you want to click on the button Import from Material Library. And under the Material Library, you can see there is a filter section on the left-hand side here. So you can see you can filter by region. So we have a long list of regions that you can pick from to find your material. For this training, I'm just going to use some US materials. So I'm going to click on United States, and then I'm going to click on material type, concrete. And so then once I filter to the material type that I would like, you can see for concrete, there's the subtype of material. I'm just going to choose regular old concrete. And then the standard, we have the ACI for the American standard for concrete. You can see I can choose between different older standards or the newest standard. I'm just going to choose the newest one. And then on the right-hand side, we can choose the compressive strength of this concrete. We're going to choose 4,000 PSI. Now, an easier way to do this is you can also just use the search function down here, and you can, let's say I clear my filter here. I can simply type in concrete there, and then I can find concrete here and for the ACI and choose the compressive strength. So we'll stick with that. So we chose concrete, 4,000 PSI. And the next thing I want to do is, for example purposes, we can edit this material by clicking on this edit button here. And once our edit material dialog box pops up, what I want to do is turn this material into a user-defined material, and I want to set my Poisson's ratio to 0, and so this will give us equal distribution of our results across our surface, and then we can click OK. And this will help later on when evaluating our results. So now what we need to do is just click OK. Click OK again. And so once we click OK through all those boxes here, now you can see my cursor has changed to this reticle. And you can see that I am snapping to each one of these grid points here. So this will help me draw to the exact dimension to 1 foot the surface. You can also turn off the snap settings down here with this button. So you can turn those off and on. And you can right click and see right click here and see all of the different snap options. And this is similar to AutoCAD in a sense. So we're going to first snap to the origin here. So I'm going to left click on the origin, and this first surface is going to be 32 feet by 16 feet. So I'm going to go 32 feet in the X direction, and then 16 feet in height. And with the rectangular surface, all you need to do is define 2 corners. And so now you can see my surface is defined. And now all I need to do is either hit escape, or I can right click anywhere and simply exit out of that tool. Now the next thing we want to do is draw a line down the center, directly in the middle of this surface. And to do that, we can go up here to the option New Line. And so that you'll see the New Line tool will pop up, and now I can simply snap to the center of the top of this line here, left click, and just draw this line on top of this surface like so. So that's how you can create a new line and draw a new line. So we can right click out of that and right click again to exit fully out of that tool. And now you may notice that these nodes here are a different color compared to the corner nodes here. And if we double click on one of these nodes to edit them, this is something I just want to go over real quick, is that these nodes are set to the node type online. And what this means is if I click OK, this means that these nodes are integrated into the line that they're connecting to. So if I double click on this line and edit it up here, and I go to the tab here, Nodes Online, you can see that the node is being recognized and connected to the line that I'm editing. So if this node was set to just the normal standard type that nodes are usually set to, they wouldn't be integrated into the line they're connecting to. So this is done automatically, but just good for your knowledge to know that there's different node types. Now, the next thing we want to do, now that we have our concrete surface here, is we want to support it. So what we can do to add in our supports here, so we want to continuously support the left-hand side of this plate here. So that means I want to add a line support to this line here on the left-hand side. So to do that, we can double click on it to edit it. And then we have a list of options here. We want to add a support to the line. So that means this tab support here will pop up. And then under line support, we can hit this drop down. And you can see we have a couple of preset definitions for what our line support should be. I want this to be a hinged line support, and a hinged line support means that the first 3 degrees of freedom, or translation degrees of freedom, are fixed, so the support can't move in the X, Y, or Z directions, but rotation is fully released, so that is a hinge support, and this is what it's going to look like. So we'll click OK, and click OK again, and now you can see if I rotate the model, we have our side here fully supported by those hinge supports. So also another thing to point out is if I double click on my line here with an RFEM, you will always see the nodes that are making up your line, or also if I edit this line support here, you always see the assigned line that goes with this line support. So with an RFEM, you're always going to know what objects are connected to each other by this upper right hand corner here, and that kind of helps you understand what's connected to what. So always clear there. So now we can highlight our other 2 lines here, which we would like to add supports to. So if I hold Control and I just select these lines, there's also a button up here called Assign Line Support. So I'm just going to select that tool, and RFEM is going to remember my selection before I clicked on that tool. You can see lines 3 and 5 here are selected. And what I want to do now is none of these presets here are the definition of line support that I want. So I can create my own definition by clicking on the new definition button here. And this support, I want it to be able to slide in the translational X direction. So I'm going to uncheck UX here, which fully releases the direction in the global X direction, but you can see it's still supported in the Y and Z direction, and rotation is still fully released about the X, Y, and Z axes as well. So I'm going to click OK, click OK again, and now you can see those supports are added to my lines there. Next thing we want to do is now create a surface load, but before we can do that, it is very important to know that any loading that you apply to your structure must have a load case assigned to it or associated with it. So the next thing we want to do is create a new load case. So you can see we already have our LC1 load case here already created by default. The program will always create or have a load case that's already created. So what we really can do is just click on the edit active load case here to look at that. So this is where you can create load cases. You can have multiple load cases, and these will go into your combinations. We're not going to get into that this training. We're just going to focus on one single load case here. It has no action associated with it. We don't need to worry about that since we're not doing any design or anything like that, or load combinations. So what we can do is just deactivate self-weight here on the right-hand side and just delete the name of this load case. So it'll just be called LC1. That's how we will refer to it. And again, I deactivated the self-weight since we don't want to take that into consideration, since we're going to focus mostly on how you can compare your models to your hand calculations, for example. So now what I want to do is just click OK. And now I want to add a surface load or area load to the top of this plate here. And to do that, it's very easy. You can just go up here to the tool, new surface load. And with this tool, we can define our new surface load. So we want the load type to be a force. We want it to be uniform, and we want it to reference the global X, Y, and Z axes. And so that means we want the direction of this load to be in the global Z on true area direction. So the loading, we just need to give it a magnitude. It's going to have a magnitude of negative 0.25 KSF, or kips per square foot. And we give it a negative, so it acts into the negative direction. So we'll click OK. And then all I need to do is tell the program which surface to assign this to. So we'll assign it to this first surface here. And now you can see visibly or graphically our loading here. Something else you can do is right click on this loading and you can adjust the size of it using this slider here if you would wish to do so. So yeah. So now we have our plate here, it's supported, it's loaded. Next thing I want to go over is now the FE mesh settings, which are very important if you have a surface or any surfaces in your model. So to access the FE mesh settings, we can go up here to this button, hit this drop down, and we can access the what's called the mesh settings here. And this is always important to look at before you run any results. You can see these are the general settings, and right now under target length of finite elements, this is set to 1.64 feet, and this is going to be the global length that a finite element is set to throughout your entire model. So if this isn't changed, then this is going to be the length of your finite element. We're going to leave this as this length for now because we're going to add in what's called an FE mesh refinement. So with an FE mesh refinement, we can specifically tell the program for a specific surface what we want the FE mesh length to be. And so to do that, we can go into the navigator here on the left-hand side and create an FE mesh refinement. And to do that, we can go under types for surfaces, this folder here, and you can see there's a couple different types. This surface, what we want to add is a surface mesh refinement. So we'll right click on that and we'll click on the option here, new surface mesh refinement. This box will pop up and we want to create a new refinement. And so we're basically telling the program we want this surface to have an FE length of 7 feet. So we're going to create a couple refinements. This first refinement is going to be 7 feet as the target FE length. Then I'm going to define another refinement. This next refinement is going to be 4 feet. I'm going to make a third, and that one's going to be 1.25 feet. And then I'm going to make a fourth refinement definition, and that's going to be 0.4 feet. So normally you would want to assign these refinements to a surface. We're not going to do that just yet. We're going to click OK. And the next thing I want to do is make a copy of my surface here. So I'm going to highlight the whole thing here, and I'm going to use what's called our move/copy tool. With this tool, you can move something or make a copy of it, or do both at the same time, which is what we're going to do. We're going to create a copy, and we're going to create 3 copies of the surface. And we want to displace them 37 feet into the X direction. And what this allows for is to be a 5-foot spacing between each of these copies, since the surface is 32 feet long. And so now all we need to do is hit OK. And now you can see I made 3 more copies of my surface here with all these supports and everything, and they're each 5 foot spaced apart. So now with our copies made, now we want to create our single member, or our beam member, that we're going to use to compare results to. Now to do that, you can see that my grid here is, we're going off my grid here a little bit, so I'm just going to highlight all of these plates, and I'm just going to drag them to the left a little bit so we have some space here on the right hand side to model the member. So I'm going to hit reverse z-axis direction, and then I'm going to go up here to the button create new member. Under new member, we're going to use the member type beam. This member type allows the member to take tension and compression forces and have fully fixed connections. What we want to do now is tell the program what cross-section this member is going to have and what material it's going to be made of. So to define the cross-section, we can just go down here to section with material and click on this button, import from section library. Now here is the cross-section library that's in RFEM 6. You have different categories here. As you can see, the category we're going to be focused on is the massive category here, which is where we can choose our massive rectangle section. And with this section, you can see we can define our material here. I already defined or had a preset of our concrete 4000 PSI material, our isotropic linear elastic material here. And if this wasn't already defined, again, you can click on the material library, and this is the same material library throughout that we've looked at from the surface. Next thing we want to define is the parametric massive, or we want to define the dimensions. So we're going to go under the parametric massive tab here. And so I'm going to define the base, which is going to be 40 inches. And then the depth of the section is going to be 12 inches. So you can see how this is going to be similar in depth to our surface, which is what we're going to be comparing to. So with that defined, we can click OK and click OK again. And now I can just draw my member, just like how I drew that line from before. And so I'm going to just start drawing it 5 feet away from our plate here, right in the center. And I want this member to be the same length as the plate, which was 16 feet. So I can draw that 16 feet, or I can just type it on my keyboard without moving my mouse, 16 feet, and hit enter. And I actually wanted to make that 32 feet. Sorry about that. So Control Z real quick. And I'm going to, let's see, draw that one more time. I actually wanted that to be 32 feet. There we go. Then I can right click, and now you can see we have our member here drawn the same length as our plates here. Now with this member, it's just floating in space right now, so we need to support it. I want to add a support directly in the middle of it. To do that, I need to add a node. So what I can do is divide this member by right-clicking on it, and you'll see my shortcuts menu will pop up when I right-click here. I want to go under member, divide member by a number of intermediate nodes here. Really need to divide it by one node, so we're adding a node to the middle of the member. But one critical option to turn on before doing this is we want to create this node on member, so that adds the node to the member without dividing it. So we don't want to divide the member, we want to keep it as one single 32-foot long member, just with a node in the middle. So we'll turn that option on, where we only want to divide it by one node, click OK. And now it's a little hard to see that node, but it's right there. So now if I just highlight this first node here, we want to add our nodal supports. So I'm going to go up here to nodal support instead of line support, since this is for nodes. We'll click on nodal support. And we want this support to actually not just be a hinge support. You can see we have some presets here for nodal supports. We're going to want to create our own definition here, and I will explain why in just a little bit. But we want all of our translational degrees of freedom to be fully fixed, but we also want our rotation about the local x-axis of our member, or about the global x-axis of our member, to be fixed as well. So we're going to click OK. Click OK again, and so now you can see that support, the rotation about the x-axis is fixed there. And now we're going to add in our other supports. So our other two supports for the middle and end of our member are going to be rolling supports that are allowed to roll or move along the global x-axis here. So we'll click OK. Oh, I just changed the support by accident. Let's just undo that. So again, we're going to choose rolling support. And with this, now we can just assign our support to our nodes here. So these supports, so the reason we needed to fix the rotation of the local x-axis for this one is if we didn't do that and all of these had the rotation fully released for all 3 degrees of freedom, this member would be allowed to spin about its own local x-axis indefinitely, causing an instability in the program. So always keep that in mind when you have a member that can has torsion fully released on it, as that can cause an instability in the program. Next thing we want to do is add in a load. We want to load this member. So we'll go up here to new member load, similar to new surface load. And we want to add an equivalent load to our surface load, and that's going to be negative 0.210 or 0.21 kip per feet. And again, this force, it's going to be a force, a uniform force, and act in the global z-axis here. So we'll click OK, and now we can just assign our load to this member and click OK. And now you can see we have our loading there, our uniform load onto our member. So now what I want to do is, before we take a break and get to questions, is I just want to Actually, let's take a break now since it's 2 o'clock, and then we can get back to this model. So before we take the break though, I would like to ask Siska if there are any questions that came up that were asked, and then we can get into the break.
Hey, Alex. We only have 2 questions. The
Okay.
first one is, when can they expect to see the recording of the webinar?
Okay, yeah, that's a good question. So the recording of this webinar will be sent out. You should expect the recording to be sent out at the beginning of next week. So the recording will be sent out along with the materials such as these models that I'm going through and this PowerPoint. So that's a good question.
And the second one is, how to display the result values on the surface.
Okay, yeah, so that question, since we haven't gotten to the results of the surface yet, we can get into right after the break since we'll be running the results right after then. So I will answer that question once we get into the results. But that's a good question. So is that all of them?
Yeah, that's all.
Okay, awesome. Thanks, Siska. So yeah, we'll take a 5-minute break. So we'll come back here. So we'll meet back here in 5 minutes. So everyone use the bathroom or get a drink or something. All right, so let's jump right back into it. Looks like some of you are coming back. All right, cool. So yeah, so now we have what we just did was add in our supports and loading to our beam here on the right hand side. And now what we want to do is I want to show you is how to assign mesh refinements, and then we can generate the FE mesh. So I'm just going to up here with this button, turn off the loading. And since we created those mesh refinements, you can see them here in the navigator. So if I go to surface mesh refinements, you can see those definitions that we created under here. And the reason that they are blue right now is because they are not assigned to any surface. So if you ever see data in the left-hand side here and it's blue, anytime that means that it's not assigned to any element in the model. So what we want to do is I'm just going to right-click on surface mesh refinements, hit edit, and go through here and assign them to our surfaces. So we're going to assign this first one to our first surface, and you can see we can do that graphically by hitting the button there and clicking on our first surface, clicking OK. We can do the same thing for our second refinement. Select surface here, select our second surface, and then for our third one, again, we can do the same thing graphically, or if we know the number of our surface here, we can just type in 3, since this is surface 3 here, and then type in 4 for our last refinement, and hit OK. So now they change from blue to normal default color, and you can see we have these icons here now on top of our surfaces. And this is how you know these icons here, or how you know that there's a surface mesh refinement on top of our surfaces here. So now that we have those refinements, we can generate the FE mesh. And so to generate the FE mesh, you can do this manually. Normally this is just done once you run your results, but you can generate this mesh manually. So if we go up here to this drop down here and hit generate FE mesh, this will run the solver, and then our mesh will be displayed on our surfaces here. It's hard to see because our surfaces are gray and there's a grid. So what I can do here is just turn off the display of the grid since we don't need it anymore. And I can turn the rendering from a transparent model to wireframe model. So now you can see our continuous beam here is just simply a one-dimensional 1D line here, just with material and cross-section properties applied to it. And you can see our frames of our surfaces here with dotted lines. And you can also get a better look at our FE mesh. So you can see gradually as we move from left to right here, our FE mesh gets pretty wonky, or starts out pretty wonky. And then the smaller the finite element gets, the finer our mesh gets and starts to look a lot better. So this is as we, from left to right, decrease the size. This first size was 7 feet, and you can see it goes from 4 feet to 1.25 feet and gets smaller and smaller. So this first surface here, I would expect very inaccurate results from this surface. And as we move from left to right, the quality gets better, and I would expect very accurate results from surface 4 here on the right hand side. So the next thing we want to do now that we created our FE mesh is add in a results section that will cut through our surfaces here and create a results section. So to do this, we can go up here to this button, set new results section. And to set a new results section, we can simply type in, it just needs 2 points, point A and point B, or 1 point and 2 points. We can click on this button up here, select 2 points graphically, and you can see I can snap to the center of my first surface here. And I'm going to draw this results section all the way through all of these surfaces here. So now we'll have a plane, a result plane section cut through all of our surfaces. And this is based on the global coordinate system, and it's going to be set in our local z-axes. So that's where the plane will be located, projection direction, and we can click OK. And now you can see we have these arrows here for our section cut. So it is in the global z-axis plane, and that's how our results will be shown. So now we can calculate our results. We can go up here to this button called Calculate All. I'm going to click that, and RFEM will run through the solver and go through that FEA workflow that we talked about earlier and give us our results. Right now it is showing us the deformations, and also you'll see the results tab will pop up here. And whenever you run your results, I always recommend taking a look at the global deformations first. This is always just an easy first visual way to check that everything is defined correctly and everything looks as you would expect. So if I look in this side view here of our model, the deformations are looking good, and they're looking just as we would expect them, or how we would expect them to look. Now, whether this side is accurate or not is up for discussion, but the internal forces are also the next thing we can take a look at. So we can turn off global deformations up here and check on members here. And once we check on members, or actually before we check on the results for the members, what we want to do is compare the results of our last section here with the results of our beam here. So what I'm going to do is go up here, or I'm going to select my surface here and select my beam. And what I can do is create a visibility by selected objects using this button. And now you can see the other objects have been grayed out in the background, and now the only ones visible are the plate here and the beam. And what I'm about to show you is very important. So if we take a look at the results on the member, so I'm going to check those on. You can see, one second. That my internal forces should be shown. Oh, so what we need to do is check on moment. So we have checked on the results for members, and then under the internal forces here, we want to check on moments about the local y-axis. So that's what's being shown right here on our member, is the moment about the local y-axis of our member. So if you ever need to see what the local axis of the member is, how it is oriented, you can right click on any member and you can turn on the local axis system of the member. And so now you can see what that local axis system looks like right on the member, and you can see the moment distribution about the y-axis here. Let me turn that on. Now I want to turn on the internal forces, or we want to look at the moment distribution of our surface here. So I'm going to check on results for surface, and then I'm going to go down here under the internal forces category, and I'm going to check on MX for basic internal forces. So mx here, again, lowercase letter, so lowercase x. This means that for the surface, these are our bending moments and the direction of the local x-axis of the surface here. So if I right-click on the surface, I can turn on the local axis system, and you can see the direction of that. And so we're showing the moments along that axis. And so now if I turn on my results section, or I'm going to have to cancel out of this visibility. If I select these plates and members, there we go. So now you can see we can compare directly the moments of the moment distribution between our beam and our plate here. And these should be basically the same. So I'm going to also turn on results sections down here, turn on local extremes. So you can see that we have our results here, and they should be pretty close to the beam. And also we can show our shear force distribution as well. So I'm going to turn on the shear force in the Z direction, and then turn on the shear force for our surface in the X direction. And yeah, so we can compare those two. So I was wondering why our results are a little off here. So you can see I typed in the wrong magnitude here for either the surface or the plate here. So I'm just going to change this to negative 0.25. And then rerun that calculation real quick. And we should see better comparison between those two elements. Okay, so now you can see we have a max shear force here of 2.4995 and a max shear force here of 2.499. So you can see between our plate and our beam here, we're getting very similar results. So this is how you can view the internal forces of a plate or beam. And I just want you to keep in mind for these values, or for these forces here, what the lowercase axis symbol shows, and these all refer to the local axis system of what they're showing, so for surface and beam. So I'm going to clear those visibilities. Also, there was a question about how to show the values on the surface or on a surface, so I'm going to show that real quick. To show the values on a surface, we can simply go down here to values on surface and check that on. And then you can see that the value is shown for each, if we go down here to result values, or we have to go to, if I can find it, it's fine. So we have values of surface turned on, and then right here under values on surfaces, right now each value is set to a grid point. We can also change this to each FE mesh point, and you can also turn on symbols and numbering. So right now this is showing the shear in the X direction, so each of these is the shear that the surface is experiencing at that point. So always good to know how to view the values on a surface there. And now we can move on to taking a closer look at our results sections for each of our plate here. So I'm going to go up here and turn on or look back at the bending moment for each of our plates here. So if we take a look at each plate here, you can see that the bending moment is different for each one here. Starting with this plate here, we have about 10 kip per feet, or 10 kip foot, and you can see how that's decreasing, and each plate here with an increasing or decreasing mesh size is getting closer and closer to our control of our member here, which is what the result should be closer to. So you can see how inaccurate the results here of this plate with the larger and super coarse mesh size. So this shows the importance to making sure that your FE mesh is as fine as necessary, but as coarse as possible, because if you don't check on your FE mesh before running results, they can be inaccurate. But also, it's important to keep in mind that if your FE mesh is too fine, such as this last plate here, this is an example, if it's too fine, this can increase your calculation time. So if you have a large model and you have too fine of a mesh, your calculation time can greatly increase. So what I recommend is something like this third example here would be closer to an FE mesh where it's fine as necessary, but as coarse as possible. And another good rule of thumb to keep in mind is to have at least 4 FE mesh blocks between any span or boundary of your surface. So 4 FE mesh blocks between any line here is usually probably the minimum you want your mesh to be at. So something like this would be too coarse, where we only have about 3 FE mesh blocks, or is that we have 4. So this would be about the minimum of how fine you would want your mesh to be. But as you can see, the finer the mesh, the more accurate the results. So next thing to look at real quick is we can also take a look at the result diagram of our section here. So if we right click on our section, we can take a look at the result diagram. So right now we're looking at the internal forces mx along our result section here. And this is just interesting because you can see what increasing your mesh size and decreasing your mesh size does, and having a finer mesh, as it adds more data points along this line here. And you can see the more data points, the better looking our member or our moment diagram starts to look. So you can see it starts off very rough and then gets finer and finer. So we can also, now I'd like to get into talking about shear stiffness. So with shear stiffness, such as for this beam, for example, if you wanted to compare hand calculations for this beam, if you want to run do hand calculations and compare them, you would have to take into account shear stiffness effects. Now, taking into account shear stiffness leads to things like the increased deformation due to increased shear forces, and that also leads to, in turn, increased moments. So this plays also a major role with things like concrete, because the thicker something is, the more shear stiffness effects you will have, or shear stiffness deformation effects you will have. So and this is all taken into account by default, I would just like to mention, by RFEM, so this is nothing you need to change, just something to keep in mind that shear stiffness effects are taken into account. So normally with hand calculations, you would assume that that the shear stiffness of something is completely rigid. Now, if you wanted to compare hand calculations or deactivate this effect, you could right click or double click and edit this member, for example. And we could go under the section tab here and edit the member start here. And then there's an option here called deactivate shear stiffness. So keep in mind, well, so if we deactivate shear stiffness and click OK, the program's going to ask us to, or tell us this is going to require us to delete the results. We'll click yes, click OK again, and now we can run our results again, and we should see our results change based on checking off this option. So now you can see we have an increased moment here a little bit. Results haven't changed too much, but you can see the moment has increased by a little bit. And this is because we deactivated the shear stiffness, or taking it into account with this beam. So now I would like to just give another question or another poll. So I'm going to throw that up on the screen now, and you should see that in just a second. So I'll give everybody a minute to answer this question, and then we can go over the results and answer afterwards. All right, so it looks like most of you voted, so I'm going to close this and then share it. So now we can see the results. So the statement is the FE mesh size should be, it should be as fine as necessary and as coarse as possible. Second option, as coarse as necessary and as fine as possible, or as precise as possible and as coarse as necessary. So the correct answer is as fine as necessary and as coarse as possible. And the reason for this is because you want your FE mesh to be as fine as it needs to be, and you also don't want it to be too fine where your calculation time is greatly increased because of how fine you made your FE mesh. At some point, you're going past a threshold of where it's worth it to have a super fine FE mesh, but also increase the calculation time, because so you hit a point where the results aren't really getting any more accurate and you are increasing your calc time. So as fine as necessary, as fine as it needs to be, but you want to make it as coarse as you can. So that's the correct answer and how you want to define your FE mesh with FEA software. So I'm going to hide that. And now we're going to move on to the next subject, which is plate theory, which kind of leads off of talking about shear stiffness. So I'm going to hop back into the PowerPoint here. And we can get into plate theory. So before we get into plate theory, I would like to give an analogy to, or make an analogy between plate theory and two theories for beam elements. So the first theory for beam elements is Bernoulli's, and with Bernoulli's we are making, and then with that, the other second theory from Bernoulli's is the Timoshenko theory, or what's also called the deep beam theory. So with the Bernoulli's theory, we're making some assumptions, and these assumptions are first that the that the cross section remains in plane and also perpendicular to the member axes. And the second assumption is that we do not consider any shear deformations. And what this means is that the shear stiffness of the beam is completely rigid. So that's the assumptions that are made with Bernoulli's theory, and this is what you're probably familiar with when running or doing hand calculations. The assumptions we make with the Timoshenko theory is that the cross sections remain in plane, but they don't remain perpendicular to the member axes. So the shear deformations are taken into consideration here, and the shear stiffness is limited and is not completely rigid. So this is the more realistic approach, and also you can see down here that we're not only taking into consideration just the deformations from bending, but also we're taking into consideration deformations from shear as well. So there is a graphic here. So for Bernoulli's, with this graphic, you can see that the shear deformations are perpendicular to the member axes here, which is what we assume for Bernoulli's theory. But with the Timoshenko theory, you can see that we have an additional angle here. And so this means that we are going to have additional deformation, and this is due to the additional shear deformation or shear stiffness being limited. So as the member deforms, the angle changes, and we are just going to have additional shear forces. So again, this is because we're taking into consideration shear stiffness for Timoshenko theory, but not for Bernoulli's. So these two theories have their differences, but they are comparable to the plate theories. So this is why I want to talk about them. You can compare them. So a similar theory to Bernoulli's theory is the Kirchhoff's plate theory. And similar to the Timoshenko theory is the Resner-Mindlin theory, which works the same for plates. So here are the assumptions. So for Kirchhoff's theory, we assume a geometrically linear or small deformation analysis. We assume that a linear elastic material is used, so we're referring to Hooke's law. We're also assuming that the cross-section remains flat and there's no warping of this plate. The plate has a constant thickness. And we're also assuming, which is the biggest assumption, is that there's no consideration of shear deformations. And that's with Kirchhoff's theory. Now, maybe you'll be able to guess, but with the Resner-Mindlin theory, we're assuming all of these same assumptions basically, but the major difference is that we are taking into consideration shear deformations, but including this, we are taking into consideration transverse and lateral strains. And so to clarify a little bit more on transverse and lateral strains, we can go to the next slide here. And here we can get a better look at what the transverse and lateral strains look like. So here we have one beam, and when a tension force is applied to this beam along its length, the cross-section will shrink, and this is with regards or with respect to the height and the width. And you can see on the right hand side here we have the mu factor, and this is what takes into consideration the shrinkage of our dimensions as the strain is, or as the force is being applied to our beam. So again, just to summarize, Kirchhoff's theory for plate theory, this yields pretty good results when using very thin plates, for example, concrete slabs. Like the ones we're using in our example. But you have to keep in mind that this only considers pure bending load bearing capacity, and this is just a simplified approach, but works fairly well for thin plates. Again, no consideration of shear deformations with the Kirchhoff theory as well. So Resler-Mindlin theory, on the other hand, though, great for thin plates and thick plates. So the thicker the plate gets, the more or the bigger the delta you'll see and the difference of results, and the more inaccurate Kirchhoff's theory becomes because of the shear deformations. The effect of shear deformations will greatly affect the thicker plates. And so in my opinion, the Resner-Mindlin theory should just be used by default, but it's just good to know the difference between the two. Now we can go back into RFEM and look at where these settings are located. So I'm going to switch back to RFEM. And if we go under the navigator here and we go under data, we can go under the load cases and combinations here and go under the static analysis settings, and we'll just go under the geometrically linear settings and edit these. And if we edit them, we can go under basic settings here, and you can see that the plate bending theory here, you can change between Mindlin or the Kirchhoff theory. Like I said, Mindlin should just be used by default, but it's just good for your knowledge to know that we have the option between these two theories. So if, for example, if we change, so if you look at the values here, if we change this to the Kirchhoff theory, it's going to ask us to delete the results. We can just rerun these real quick. Click yes. And we're probably not going to see too much of a difference in results because we have thinner plates here. So the results are going to be pretty similar, but you can see that now our results are more on this last plate here, are closer again to our beam now that we're not considering shear deformations. If we had thicker plates, like some foundation plates, for example, we'd probably see a bigger delta between these results. So now I have another question to post. I'm going to throw that up now, and we can go over the results in just a little bit. All right, so I'm going to close that question and share the results. Awesome, everyone got this one correct. So the Kirchhoff theory does not consider shear deformations. That is true. The Midland theory does consider shear deformation, so great job. All right, I'm gonna hide that. And I just want to also give another poll and ask everybody if the pace is okay, if you guys want me to speed up, slow down. Yeah, so I'm just gonna put that up there and gauge that. All right, so looks like the pace is all good. Cool. So I'm gonna hide that. And then now we're going to get into our next topic. So I'm going to switch back to the PowerPoint. And our next topic is nonlinear calculations. So we're going to talk about nonlinear calculations with an FEA. So the disadvantage to using a nonlinear calculation is that the superposition law is no longer valid, basically. Usually superposition law would be valid with a linear calculation, but with a nonlinear, it's not. So typical application areas in RFEM 6 where nonlinear calculations would be used include geometrically nonlinear calculations, and these take into account or take into effect second order behaviors such as little and big p delta effects. Next is nonlinear material behaviors. So this takes into account things like yield strength. And so you might have done some yield strength tests in your class or in a lab with a steel sample, and you can see how the stress strain graph is normally linear with respect to stress and strain, and this can become nonlinear and when it enters the plastic region. And so this is an example of where nonlinear materials would be considered, and there's also some examples of nonlinear materials like glass, silicone, and cable elements where their stiffness changes depending on the forces applied to them. Then we have nonlinear behaviors for structural objects or structural elements such as members, hinges, or supports, for example. And we'll be getting into examples of these nonlinear behaviors in just a second. So yeah, keep in mind that these types of calcs or type of calculations can increase the accuracy of your calculation or of your model, but also at a large scale can increase the calculation efforts and time, similar to your FE mesh. So the more accurate you want your model to be, the more time it spent calculating. So we're going to go back to RFEM and look at some examples of these nonlinear calculations. So I set up another model. I'm going to open that right now. So we're going to open this model. And again, these models are going to be provided to you guys. You'll get them with the recording early next week or the beginning of next week. So I would expect these to show up on your end at that time. But so for this model, I set up a frame, and this frame has some tension only members in it. So if I double click on one of these members here on this cable element from this X bracing, you can see that the member type here is set to tension. And so with this frame, we're going to just imagine that the top of this frame here is connected to another building. I'm going to turn off the grid here so we can imagine that the top here is connected and braced by another building. And so we need to basically brace this wall in the global X direction here. And this is the reason why we needed to add this X bracing in. So, like I said, this X bracing, we're assuming that these elements can only take tension, almost like a cable element where the cable or rope just cannot take compression forces. And this is a nonlinear element, meaning that it can only take tension. So let's just see what happens when I take this model. I'll highlight and just delete these cable elements. And we can see what happens to our calculation. When I run it, if I turn on my load here, you can see we have a wind load applied to here, to this frame in the X direction. And let's just see what happens. So you'll see an error pops up. Some errors and warnings occurred during the calculation. And the reason for this, we would call this an instability. You can see the stiffness matrix is singular, structure is unstable. And so the reason, well, basically RFEM does a check of the stiffness matrix, and if there is a singularity, then the structure is unstable, and it will give you this warning down here and not show you the results. And the reason for this is because our structure here is just not stable and needs support in the global x-axis here. You can see that we have all hinge supports here. These supports up here are not providing any support in the x direction, and all of our connections here are hinged, and our members up here at the top are truss members, meaning that the moments at these connection points are fully released. So this whole model is just not supported in the global x direction. So what we need to do is stabilize this model. And how can we stabilize it? We can do that by adding in X bracing. So I can go up here to new single member, and under new single member, you can see we have member types. So we have beam. Beam type is the type you are going to be most familiar with. This can take tension and compression and has fully fixed connection points, meaning moments and shear forces are transferred between connections. We have a truss type here, which can take tension. It can only take axial forces like tension and compression, but it can't take, or just the connection points are fully released, so no moments are transferred between connections. And then we have our tension members. And our tension members can only take tension and cannot take compression. So these are our nonlinear members here. And what we want to do is go into our section here and change our cross section to a 1/4 of an inch round section here, which will act as our cable element. So we'll click OK. And now we can draw back in our X bracing here and do that like so. I'm going to right click, and now I can simply just take this X bracing that I've applied here, highlight it, hold Control to copy it. I can just take this, move it over while holding Control and copy it. Well, it's supposed to copy, I need to keep holding Control, so let's do that again. Let go of Control. So now we have our copy there. And so, yeah, now we have our X bracing. So now this structure is braced in the X direction. And so now let's try running our results again. So now you can see that we have our results now. And if we take a look at our deformations, we can turn off our loading. You can see that this member right here has extended since this structure is, there's a wind load on it being forced into the X direction. You can see that this cable element is still activated and taking on those tension forces. But this one here has been grayed out and is not, and has been disabled because it's taking compression and it cannot do that. And you can see the same thing for this tension element on the right-hand side. We can also take a look and check on the results for our members and take a look at the normal forces or axial forces. And now we can see what the axial forces are on those two cable elements that are taking the tension. So red is positive for tension. You can see the blue here is negative for compression. And then if we also take a look at our wind loads in the opposite direction, we should see the same thing. So we'll run that. And now you can see the same thing is happening if we take a look at our global deformations. The other member now is taking compression and disabling, and the opposite member is now taking the tension forces. So this is one way to use nonlinear members or elements, or have a nonlinear calculation in RFEM. So that's the end of that example. And so I have another example I would like to show you. So I'm going to open up the next model. And that's here. So this next one, we're going to be going over nonlinear supports. And so with this model, you can see here, I just have two frames here supported at the top here. And you can see that I have on the right-hand side this nodal support here in blue. And the reason why this nodal support is in blue is because it's telling me that it's a nonlinear support. So anytime you see a support that's blue and not green, that means it's a nonlinear support. Green means that it is a linear support. So let's double click on this support and see what's going on and edit it. And you can see under our definitions here, everything looks normal here. All 3 degrees of translational freedom are fixed here. Our rotation about the global z-axis is fixed. But for the x direction, we have a nonlinear set. So if I click on this drop down here under nonlinear, you can see I have checked on failure if negative px. And what this means is if this support experiences a negative support reaction, it will fail. So yeah, it'll fail, it'll disable, it won't add any support if a negative support reaction is activated. So let's see what this means when we run our results. So click OK again, and I will turn on my results. And you can see now that the deformations on the left-hand side here are pretty much almost non-existent. And that's because this force here, this support here, is absorbing all of the force that this load is providing. You can see this lateral load is pushing on the top of this frame here in the x direction. So this support is going to have a negative x support reaction, but it's a linear support. And you can see here on the right-hand side that our nonlinear support with the same setup is failing because it's experiencing that negative support reaction. And so it's disabling, and you can see how that affects our frame here. And we can also take a look at our support reactions by turning on support reactions here, and we can see those support reactions from the forces there. So before I get into the next example, it looks like we're approaching 3 o'clock, so I would just, I think we can take a break soon. So Siska, is there any questions from the chat?
Yeah, we only have one question, and
Okay.
someone asked if it's possible to assign hotkeys to a command.
Okay, yeah. Yeah, that's possible in RFEM. You can assign hotkeys to a command, which is actually pretty helpful. To do that, so let's say we wanted to change the save function, the command of the save function or something like that, you can go up here to the customize menus and toolbars, and we can go under, let's say, tools, and let's say we wanted to add a keyboard shortcut to the measure function, for example. We can do that. You can add a keyboard shortcut to any of these functions up here by just double clicking on them and then entering the function or the shortcut on your keyboard, and you can set that. And so then that's how you can assign hotkeys to any command within RFEM. So great question. Thanks, Siska.
Yep, that's all the question.
Okay, good to know. Thank you. So yeah, so we can just go into our break now. So we'll just take a 5-minute break, and we can come back here at 3:05 Eastern Standard Time. All right, so looks like it's 3:06. So yeah, let's get right back into it. I'm going to go back to RFEM. And so yeah, that was the last example that we did. So the next one, the next example to get into is going to be it's called a friction supported ladder. So I'm going to open up this next example here, and we're going to talk about friction supports. All right, so here you can see I have modeled and created this ladder here. And with each support here, you can see that each load case here has a support that's set to each step here. So I can go through each load case, and you can see that with each load case, the loading gets higher and higher on this ladder here. And the goal of this is to see if the ladder is going to receive too much vertical load and if it will slip into the X direction. So you might have noticed that the top supports here are green, so they're linear. You can also see that they are only supporting the top of this ladder in the X direction. They're not supporting it in the Y or Z direction, and they're not giving it any rotational support. So we're basically assuming that this ladder is just resting up against something, up against a wall like a normal ladder would. It's just resting up there. And we're wondering, okay, at what point will this ladder slip the higher and higher somebody climbs it? We want to make sure that the ladder, the friction at the bottom, is enough to keep this ladder from slipping out into the X direction the higher and higher somebody climbs it. So what we did is we made these supports down here nonlinear supports. So if I edit these supports by double clicking on them and looking at the definitions of them, you can see that there's no rotational support. They are fully fixed in the Z direction, so they're resting on a solid surface, but this ladder could slip out in the horizontal direction or lateral direction. So you can see in the X direction and the Y direction, we have activated the nonlinearity friction, PZ. And so activating these, you can see that now we have some new tabs up here for UX friction PZ and UY friction PZ. Now if we look at UX friction PZ, you can see that we have entered here a friction coefficient. And you can see μx, this friction coefficient, is set to 0.2. And this basically sets a maximum bearing capacity for the support. And if the reaction and the X direction exceeds the normal force, Pz, multiplied by this friction coefficient, then the support will fail. So basically the ladder will slip out either in the X direction or the Y direction. So again, this maximum bearing capacity all relies on what the normal force is multiplied by the friction coefficient. If that exceeds the reaction in the X direction, then this support will fail and give out. So let's see. So if we go click OK, let's click OK again, and let's run all of our results and see what happens when we run these results. So just looking at the deformations, we can see that for this first load case where our loading is applied to the bottom rung here. We're fine, nothing, the ladder is staying in place. But as we go to our next load case, as the force starts to go upwards, we can turn on our support reactions and kind of see how what our force is in the x direction. You can see we're at 0.03 here, and we're at 0.5 here for the normal force, 0.03 here, and as we increase our loading higher and higher, you can see that that reaction in the x direction is increasing, 0.05, and as we go higher, 0.06, 0.07, 0.08, we're getting higher and higher, 0.09, and boom, at load case 12 here, as we approach about 3 rungs down from the top of this ladder, you can see that our supports have given out, and the ladder is now slipping out because we have reached a reaction force in the x direction of 0.10 kilonewtons, and so this is exceeding our 0.2 multiplied by 0.5 here, which would be higher or lower than our vertical or our horizontal x direction here. So these supports have released and given out, and now our ladder is slipping out. So this is basically how you can use friction supports in RFEM and how useful these can be. And this is just one example of how friction supports can work and how they can slip. So moving on to another example, our next example is going to be all about plastic analysis. So I'm going to open up the next model here. So now with our next model here, this one is just basically this model is just a specimen of some sort, similar to maybe something you would see in one of your material labs. So we can just use this to go over the general concept of plastic analysis. So the elastic deformation in a structural component is due to a load and is based on Hooke's law. And Hooke's law is the linear stress and strain relationship in which most material goes through if it is a linear elastic or isotropic elastic material. So some examples of this or some examples you might want to take a look at and see what happens after the elastic behavior of the material. So maybe you're curious of what after that material is no longer elastic and has entered the plastic region, you might want to see how it's yielded and what the behavior of that component is going to be after it has yielded, and that's basically what plastic analysis is. And this is a nonlinear behavior, and to activate or to use plastic materials and RFEM, right now this material is just a isotropic elastic material. We have to go into the model, so we'll right click on in our navigator data here, we'll right click on the model and we'll go into base data, and then under base data, this is where I mentioned that the only thing we need to look at under add-ons is you would have to have this add-on for RFEM to use nonlinear or to activate nonlinear material behavior. So you have to have this add-on activated to use plastic materials and run a plastic analysis. Oh, sorry about that. Anyway, so okay. And so once we have this add-on activated, we can consider nonlinear behaviors. So we'll click OK. And we can take this, and so now we can take plastic materials into consideration. And so now let's run the calculation for this surface with some pre-made defined materials. So if I double click on this, we can see we have a thickness here of this plate or specimen. It's 3 millimeters thick. And you can see the material right now that we're going to be using is going to be an isotropic linear elastic material. You can see I have another material defined here, and this one is an isotropic plastic material. So first we'll choose the isotropic linear elastic material and click OK. And so now our material is set to that isotropic linear elastic material. It is just steel 260W. And so now with our load case here, we can just run the calculation. You can see I have a line load here applied to the end of it, and we have some supports on the left-hand side here. So this line load is going to pull this specimen in tension, and we can run the results and see what that looks like. So normally we would start off looking at the global deformations, but this isn't really the focus of this example. What we want to look at are the surface results, and more specifically, we want to filter down to the stresses on the surface. We want to filter to equivalent stresses, and then we want to take a look at our von Mises stresses. And von Mises stresses are just a kind of stress thesis that is known commonly to be used for this kind of stress design for steel sections and surfaces. And this test example, you can see this test example material this was made out of has a yield strength of 260 newtons per square millimeter. So if we double click on this real quick and we edit this material, you can see if I go under material values, strengths, or under strengths here, you can see that we have a yield stress of 260 newtons per square millimeter. So if I exit out of here and we go back to the results, we would expect that the tensile stress should be close to that yield strength. So if we want to see that this yield, we would have to take into account what the maximum loading that this specimen can handle. And so with knowing that the yield strength is 260 newtons per square meter, let's take a closer look at what this line load is, or the loading that has been applied. So you can see that the force that is required to reach the steel strength of this model is as follows. So we're assuming, or we know that the thickness of the inner neck of this specimen is 10 millimeters, and the thickness of this plate is 3 millimeters. So if we take 260 newton square meters and multiply that by the area, that will give us the maximum tension that this cross section can handle before it yields, which comes out to be 7,800 newtons. And then knowing the edge here to apply our line load to figure out what the line load should be, we can just take that 7,800 newtons and divide it by the length of that line, which is 0.014 meters or 14 millimeters. And that will give us our load magnitude of 557 0.14 kilonewtons per meter. So with that said, and with the magnitude here set, we can see and look at our results. And before we look at our results again, we also want to make sure to activate what's called result smoothing. So if I go up here to results, and then I go actually under calculate, sorry, we want to go under calculate and then result smoothing. You can see that our smoothing type right now is set to constant on elements. Normally by default, this is set to continuous within surface. And basically what constant on elements does is it shows the average value from the surrounding FE mesh points for that one single FE mesh element. And this has no interruption from the surrounding elements, so that one single element is not taking into account any of the surrounding elements. And so this is what we want to set our FE mesh to. Normally, again, by default, this is set to continuous on surfaces. And you can see how each FE mesh element can take into consideration surrounding elements, the results from surrounding elements, but we just want to know, we just want to see the average of each FE mesh point on one single FE element or finite element. So with that said, we can click OK. And so now we can see the areas of the element that are higher than 260 newtons per square millimeter. So with my control panel here, we can see the color coordination. I can zoom in a little bit more, and you can see we have that maximum loading applied, and you can see these areas in which these red and darker red areas right here at the very top around these locations, in which this plate is experiencing higher forces or stresses than 260 Newton square millimeters. And what we can do to even better see or visualize this is we can double click on the color panel here, and we can set a limit here to 260. And now you can get an even better visual of where those areas are that are being exceeded and where the material is exceeding that yield strength. So you may be thinking this is steel and it's an isotropic material, and this can happen if it exceeds that yield strength. This limit can't be exceeded. That's the yield strength. So we shouldn't be seeing, or these stresses wouldn't be shown realistically, and they wouldn't be passing 260 Newton millimeters squared. But we were getting stresses higher than that. So this is where we want to consider the material as a real nonlinear plastic material behavior. And we have to activate, like I mentioned before, the nonlinear material behavior add-on and choose a different material. So what I'm going to do is double click here, and I'm going to go into my materials that I already have preset, and I'm going to choose the same material, but instead of a linear elastic material, this is going to be a plastic material. So you can see here now, it's an isotropic plastic material. If we take a look and edit this material, we can see the different material models that we can choose from. We were just using a linear elastic material. We have isotropic plastic, and we have another longer list of other material models. We're just going to be focusing on plastic for surfaces and solids. You can see here at the top, a new tab opens for this. And you, within this tab, can set what you want the stresses to be shown as. We're going to keep them as von Mises. And then you can also set down here what the yield strength for compression and tension is going to be. So you can see here, this is 260 Newton per square meter. You actually can't, this is grayed out since this material is from a standard, but if you were defining your own material, you could set these limits here. You can also see we have the modulus of elasticity here. And then we have some diagrams on the right-hand side here, giving you more details on these limits and how the material is going to behave. So now let's run the calculation again, now that we have set our material to a plastic material, and let's see what that's going to look like. So this is interesting. So now you can see our highest stresses while viewing our von Mises stresses on the surface are 260 newtons per square millimeter. So perfect. This is awesome. This is going to, since this is a plastic material, no points on this member or on this plate should be experiencing stresses higher than 260 newton millimeters. And basically this is because now the stresses can be spread out and cannot exceed 260 newtons per square millimeter. And we can see where this plate is basically yielding. So it's hitting that max there. And then we can go over here on the left-hand side, check on criteria. And now you can see even better where this plate is yielding. Wherever 1.0 is, where this dark red is, that means these elements or these sections of this plate have fully yielded. So now let's test what happens when this, when we set a load here that is higher than the maximum, which I have done already. So if we go to LC2, you can see I have just increased this load a little higher than what the maximum should be. So we can see what happens when we run these results. So now you can see, let's take a look at the deformations of the exact limit of where this, of what this plate can handle. So you can see we have our deformations here and nothing's really deformed too much. It's just experiencing strain here in the X direction. But if we look at what happens when the limit is exceeded, you can see here that where the material has fully yielded, that the lateral strain is causing the section to shrink, and we're getting even higher deformations of 4.4 millimeters since this section here has fully yielded. And we can even play a little animation here, and you can see what the difference is between before it's yielded and what it looks like after it has yielded. So this is something similar to what you might see in your labs when doing your material testing. And these are the kind of nonlinear effects that you can consider with an RFEM 6. So now we can move on to our next subject and our last subject, which is singularities. So singularities, what are singularities? Where do they occur? Singularities are points of discontinuity in the calculation method or in the calculation model is what I mean. And this is an issue that doesn't only just occur with RFEM 6. This issue happens in all finite element analysis software. And the result will then be the result that comes out of a model with singularities or at a singularity. These results are not meaningful or plausible and should not be taken into account. So what this means is that there is an issue with how RFEM solves the model. There's no real There's no real physical issue with the structure. It's just how the software is solving the model. So this causes infinite stresses and internal forces at a singularity. So you'll see very high stresses, very high internal forces at that singularity. And so the mesh refinement, or refining your mesh, or even just increasing the mesh refinement, is not going to improve this result or help at all. It does give you, though, a better idea of the location of that singularity. So types of singularity locations, point loads and line loads and line supports can cause singularities. Openings or reentrant corners or connecting corners can cause singularities. And then stiffness changes due to a quick change to material or thickness can also cause singularities. So for the first one, I'll show you how to avoid these point loads. Then we'll talk about how to avoid or fix rounded corners or openings. And also for this third one, I won't be showing how to fix this, but a solution would be to space out or have smaller changes in thickness to a plate or something. So let's go back to RFEM, and we can begin to model this first example. So the model name is going to be singularity point load. And so, yeah, we have our model name. This model is going to be 3D. We'll keep it 3D. We're going to turn off our combination wizard and load wizards. So we'll turn those off. And so everything else we can keep as default. Our global and local axes are oriented correctly. Everything else here we can leave as so. We'll click OK. And now you'll see our grid here, 50 by 50. Let's check our units. We will switch our units to imperial. And so now we have our grid spacing and imperial. We have all of our units in imperial, and we have our grid spacing as 1 foot by 1 foot, 50 by 50. And now what we want to do is just create a concrete surface, kind of like what we did before. So I'm going to create a new thickness. You can see we have some materials and thickness carried over from previous examples. So I'm going to click on new material. This is going to open up the material library. And so now I'm just going to type in concrete. I'm just going to make this concrete 4,000 PSI. And click OK. And we want the thickness of this to be arbitrarily 12 inches. Okay. And now we just need to draw out our surface here. It's going to be similar to the plates we've drawn earlier. So we're just going to make it 32 by 16. And now what we want to do is add a node directly in the middle here. So to do this, the easiest way to do this is we have a tool up here under new node called between two nodes. So I can click on that, and all I need to do is click on my two nodes here and click apply. And so now I have a node directly between those two nodes at the center. And what we want to do is add a point load to that. And so now I'm adding a point load directly at the center of my concrete surface here. Set that to, this point load's going to be negative 10 kips in the global z direction. And so we can apply that right to the center there. And then we can just add line supports. We just need to support this now. So we're just going to support the entire edge of this plate here. So I can just highlight the whole thing, go to line support, choose the preset hinged, and now we can make 4 copies of this. So we can highlight it, right click on it, move / copy, create copy. We want 4 of these, so we'll make 3 additional copies, spaced out at 37 feet in the X direction. And then if we didn't want to move our plates over, there's another option under grid settings to have the grid dynamically change according to the size of your model. So we could choose that. So now you can see our grid here has dynamically rearranged itself to our model. We don't really need the grid anymore, so we can deactivate that. And then now we can create some FE mesh refinements. Another way to do that is we can go under structure here, basic objects. I just want to show you how to create these FE mesh refinements through the table or how to use the table. So structure, we can go under types for surfaces here. And then we can find the tab surface mesh refinements. And RFEM wants me to save. Always good to save. Never want to have something happen and you don't have your model saved. There's always backups created, but always good to save often. Target FE length is going to be, for this first mesh refinement, 7. And then we're going to make 1.4, 1.25, and 0.4 feet. And now, since we know this is surface 1, I can turn on the numbering if I just want to see the numbering displayed real quick. Missing it. Show numbering. So now we can see surface 1, 2, 3, and 4. So we want to assign the 7 feet to 1, 2, 3, and 4. So now our refinements were created here and we assign them to our surface. And so now we just want to create a results section through our surfaces. So we're going to define that. Click OK. So you can see our LC1 here. We want to edit that to not take into consideration self-weight. So let's deactivate that. We'll just not have a name for it. And now let's run our calculation, see what happens. So once our calculation runs, we'll get a better idea of what this all looks like. So first, before we look at anything, let's make sure results sections are activated, which they are. And then we want to go down here to our result views under results sections here, and we want to activate local extremes. So now we can see the extreme of each surface here. And our deformations look okay. They look good. Nothing out of the ordinary here, so that's all right. Again, you can see our FE mesh there. Let's take a look at our bending moments on our surface here. So I'm going to activate surface results, moments along the local x-axis, and we can see our bending moments there. We have on the left-hand side here negative 2.9 kip feet, and we have a maximum over here of negative 5.59 kip feet. So like we talked about earlier, we know that a finer FE mesh is better than a very coarse FE mesh like this left-hand side here. But which moment is the correct moment here? The answer is none of these. None of these moments are the correct moment. And that is because we are experiencing singularities here. And so these results are not meaningful or useful. And we cannot use these results. And it really doesn't matter what size our FE mesh is here. None of these results are good. Even this one here, that's super fine. You would think I have a super fine FE mesh here. This result has to be accurate, but it's not. It's just giving us a higher result, and it's allowing us to just see more clearly where this singularity is happening. So what's the solution? The solution is to take this point load here that's feeding directly into one single FE mesh element and distribute this point load somehow. And to distribute this point load, we can spread it out using a surface load. So we can take this load, this 10 kips, and we can pretend that this load is a column and the area of the column is 2 feet squared. So let's delete these point loads. Yes, and we want to now apply some surface loads. So before we apply the surface load, maybe it's a good idea to show you what the rendered thickness of one of these surfaces looks like. So if I go down here into the display tab, under model, I'm going to actually decrease the size. I cannot. So we're going to go under model here, rendering, model, solid model, surfaces, and we want to choose filled thickness. And you can see that the thickness of these surfaces, the center line is located directly in the middle of the thickness. So you can see what the actual thickness of these looks like. And now, and the reason it's good to know where the center line is located is because this is where the surface load is applied. And normally for concrete structures, the forces will propagate from the location of the load through the concrete at a 45-degree angle. So this is always just good to keep in mind that you need to take into account that the loading is going to be applied at the center of the thickness. So let's now create a new surface load. So we're going to create a free rectangular load. And to do that, we can go up here to new free concentrated load, hit this drop down, and click on new free rectangular load. So the load distribution is going to be uniform, and it's going to be in the global true area of the z direction. And then we're going to take our 10 kips, divide it by 2 feet squared. So that's going to give us 5 kips per square foot. And so then we just need to tell the program where the center of this rectangle is going to be. So instead of choosing the corners, we're going to choose the center of the rectangle. And to do that, we can click on select load location here. And then all we got to do is select that node in the center, tell the program that this rectangle is 2 feet by, 1.41 feet by 1.41. And now we can click OK. And then we can just click on each one of these surfaces here, click OK. And now we have our free rectangular load here. I need to give it a negative sign to flip it, and also assign to, we got to keep it at the center. It's fine. We'll click OK, flip it, and now we can just take our load here, hold Control, and just move and copy it to our other surfaces. So now we have our free rectangular load here applied to all our surfaces. So we can hit calculate. And this calculation will run. And so now we can take a look at our moments here. We got to activate, take a look at our moments here. So now we're getting no singularities because at every surface here we have similar moments. So it's not as drastic as a change, but you can see between these last two surfaces, 1.9 and 2.3, definitely a lot better than before. And this is one of the ways you can combat point loads of when they cause singularities. And again, you can see that our loading is not just feeding into one singular FE mesh point. It is being distributed across multiple FE mesh elements, which means we are avoiding a singularity issue. So it's always good to know multiple FE mesh nodes is better than just one. Another way to combat singularities is if you have a results section, what you can do is go into the result diagram, and maybe you're analyzing your results in the result diagram. There's a tool in here which allows you to smooth over results or average them out over an area, which is called smooth areas. And you can see smooth areas are turned on right now, but what we can do is edit our smooth areas, and we can choose a range. So we need to tell the program between what location and what location the smoothing needs to happen. Usually this smoothing range is based on a connecting element or a connecting column. So the range would be the length of that column. So we're just assuming our column is 2 feet squared or 1 foot by 1 foot. And so let's say we would just want to apply that smooth range on the end here on our last plate, because this is probably our most accurate results. So we would have to start it at 111.295 feet and end it at 112.705 feet. And so then the length, as you can see, is 1.141. Click OK. And now you can see that our smooth range is applied. We can also take this smooth range and we can move it throughout our result diagram here. So we can just keep that right there. This is usually just better for singularities, but as you can see the smoothed out results here, and that gives you a way to distribute the results within the result diagram. So I'm going to exit out of that. And the next example, this is the last example I have. Normally I would model through it, but we're running low on time. So I'm just going to open an already saved model that I have here, and we can go over it. So here, you can see this is similar to our last model, but with this model, we have, turn off the results here and shrink. Usually we would model through this, but we're running out of time. So I'm just going to go over this, but we have a plate here, and it has, each of these plates has a surface load applied to it. And you can see we have a nodal support connected here. So we just have this nodal support and just it's supported on this edge. And so what's happening is this nodal support, if I change it to a normal hinge support, all right, 1 second. Okay, we're just going to create a new nodal support here. We want it to just be a normal hinge support. There we go. And we'll change all of these to hinged. Okay, so if we run our results now, all we have is just this one nodal support holding up our plate here. And again, if I turn off the loading, you can see, well, we should be seeing a difference in results. I think I need to delete these. So once we run these results, we should see a singularity. There we go. Okay, so now you can see a singularity occurring at these nodal supports because there's only one point feeding into one FE mesh node, and you can see how drastic the results are, 22 versus 35 here. So you can see how drastic these results are in this, and so you always have to be careful when using nodal supports and having them support a surface like this, because since they are completely rigid supports, all of the loading is going to be fed into this one single location, and that's also going to cause a singularity. And one way to combat this is to change your supports from completely rigid to having maybe to being semi-rigid and having less of a stiffness to them. Or you can also use the smooth ranges within the result diagram. So now I'd like to just give one last question before we wrap everything up. And that's here. So I'm going to launch that. All right, awesome. Looks like mostly everyone answered, so we can go over the results. So where do singularities occur? First option was point bearing, or yeah, first option to choose was point bearings or load application, corners of walls, jumps in stiffness, material thickness, and beginning and end of line supports. So the correct answers were corners of walls, point bearings and load applications, and jumps in stiffness and material, and beginning and ends of line supports. So all of them were correct. So a little bit of a trick question there. But yeah, good to know. So now we can wrap up this training. And to wrap it up, were there any last questions that were asked in the chat, Siska, that we could
Yeah,
go over?
just one question.
Okay.
Can you show how to specify a user-defined material that's not available in the database?
Yeah, that's a good question. So we can hop back to RFEM and take a look at that real quick. So if you have a material that may not be in our database, what you can do is for a member or surface or anything, when you're defining a material, you can click on create new material. So once you click on that, you can see
Alex,
here.
can you show your
Oh,
RFM? We're still seeing the poll.
oh yeah, thanks, Cisco. Yeah, I didn't see that. Yeah,
Yep.
so sorry about that. When you click, when you're defining a or defining a surface or member, and you need to define your material, you can click on this button right here to create a new material, and then this new material dialog box will pop up, and you can see here you can define all of the basic material properties, and yeah, so that's how you can create your material.
Okay, I just want to add, okay, you can X that off that dialog box real quick.
Mm-hmm.
Yeah, here when after you define if you go to the material, can you go to the material tab to edit the material itself?
Yep.
So if you pick a material from the library, you can check the user-defined material at the bottom.
Yep. Yep.
And then you can also change the values under the material values tab.
Mm-hmm.
That's
Yeah,
the other
that's
way
true.
to do it. So,
Yeah, that's good to point out as well.
um,
Awesome. Okay.
yeah,
Was
that's
that all the
that's the
questions?
last question. Yeah, I just want to remind everyone there's a survey after they log out of the webinar, the presentation. If they can fill that out, we will really appreciate their feedback. So,
Yeah, that's a good point. Yeah, like Siska said, there will be a survey. Yeah, we would appreciate that feedback and let us know how you liked the presentation, what you would change, what you liked, and what you didn't like. Yeah, so to wrap it up, we have free online services here, which you can see. Highly recommend visiting our website to take a look at these. We also have a lot of great videos for students and also just webinars and videos on our website for learning how to use RFM. We have free student licenses. There's a form you can fill out to get a free student license. And we also offer free tech support via email and chat. So highly recommend going there. Like Siska said, fill out the form, the survey that should launch after the GoToWebinar ends. And yeah, so again, there's our email and phone number at the bottom. I encourage you to visit the website. And thank you all for attending, and hope everyone has a great rest of their week. So thank you.